Thanks a lot, Thomas, for the introduction and for inviting me to this nice conference. So in my talk, I will continue the discussion of Alessandro on vertex divergences and the breakdown of many-body perturbation theory. And I will actually speak about the relation of the multivaluedness of the Latinger-Ward functional and the divergences of the irreducible vertex functions. And I will try to highlight this connection for two very simple models in order to get more insights into the basic mechanism of this feature. So this work, which I will present today, is mainly can be mainly found in these three publications from the recent years. Alessandro already gave a rather complete introduction into the field, so I will keep my introductory slides now somehow to a minimum. However, I want to speak on my first slide still a bit about some more general perspective on the convergence of perturbation theory. So basically, already back in 1952, so soon after the invention of quantum electrodynamics and all these quantum field theories, Freeman Dyson suggested a rather simple argument that the perturbation radius, so the convergence radius of a perturbation series in QED, so this is just some illustration, has zero convergence radius. And his argument was based on his argument was based on the following consideration. So if we go from a repulsive quantum electrodynamic to an attractive one, where the electrons attract each other, which means we go from plus e squared to minus e squared, the system becomes unstable with respect to the creation of particles. So basically, infinitely many particle hole pairs will be created, and then they will separate, so not particle holes, so in QED I have to say electron and positron pairs will be created. And then they will gather together in different regions of space, because electrons attract electrons and positrons attract positrons. And that will lead to an infinite particle density in these regions of space, which is unphysical. However, if we know that we cannot converge the perturbation series for any negative e squared, it's clear that we cannot converge it for any positive e squared, since we know from the theory of complex functions that convergence appears always in a so-called convergence radius. So you cannot have any finite value of this convergence radius if you cannot converge for any negative value of e squared. And a very nice illustration, so I will just flash it, is of course a simple bosonic path integral in zero space-time, which is just a Gaussian integral with some interaction term. And of course, you can do an expansion in this lambda parameter. And indeed, then you can solve all these integrals and you get a Taylor series. However, you find that this Taylor series has zero convergence radius. And this is not surprising, because again, the same argument, if you change your lambda parameter here from a positive lambda to a negative lambda, you see that this integral from which we started does not even converge. However, the situation can get even worse than that. So we can encounter a case where the perturbation series indeed converges, but it converges to the wrong solution. And this is actually the situation which emerges in a lot of so-called bold diagrammatic theories, which are based on the Latinger-Ward functional, or better to say on its derivative, which is just the Selfenergy functional, a functional of the fully interacting Green's function. And if you complement this with the Dyson equation, you can develop an algorithm where you, from a starting guess for your Green's function, you obtain a self-energy which allows you to update your Green's function via the Dyson equation, and then you feed back this new Green's function, this new interacting Green's function into your self-energy functional in order to close this iteration cycle. So this cycle indeed converges very often, actually. However, sometimes it converges to a wrong self-energy. The origin of this phenomenon is actually the already mentioned multivaluedness of this functional. So what does this mean? So this means that for a given physical Green's function, we actually have several branches of this self-energy functional, where this n, this index n here, denotes the nth branch. And if this is not so clear, you can just think of a normal complex analysis, like a complex logarithm or a complex square root, which are just normal functions which exhibit a multivaluedness. That means they live on not on only one complex plane, but on many Riemannian sheets. From an alternative perspective, which is in some sense more practical and which is very important for what I present later, we can actually look at the map from a non-interacting Green's function G0 to an interacting Green's function G, where a physical non-interacting Green's function is just the inverse of the non-interacting Hamiltonian. So basically, if we look at this map, so we encounter several mappings. So from a given G0 to some interacting Green's function G, and how this map is done, I will not discuss in this talk. So there are several solvers like quantum Monte Carlo or exact diagonalization. So however, what you observe sometimes is that two different non-interacting Green's function can be mapped onto the same interacting Green's function of the system. That means that this map G of G0 is not injective, and that implies that the inverse map, so the map G0 of G, is multivalued. However, using the Dyson equation, this directly translates into a multivaluedness of our self-energy functional. Just a side remark here, because I often get the question, yes, but what if you just restrict your space of non-interacting Green's function to some subspace, like to the subspace of physical G0s? Indeed, if you can do that, you will get a one-to-one mapping, so a bijective mapping between G0 and G. However, in many situations, in many algorithmic situations, this is not really possible. So you will end up automatically on a wrong branch, or with on a wrong branch of sigma of G, which corresponds to an unphysical G0. And you will see this in the following for the two examples, for the two simple examples, which I will discuss for this mechanism. So let me start with this, with the first example, which is a binary disorder, within the DMFT approximation. So what is this model of a binary disorder? So basically, you have a lattice model of electrons which are hopping around via this hopping term. So this is the non-interacting part in the sense of the Green's function. And then you have an additional term, which is not really an interaction term, but it's a disorder term. So you basically have impurities which give you a disorder potential at the lattice side. So and either you have in this binary mixture a potential minus omega minus W half, which are these orange sides, or plus W half, which are these okay, I guess that are blue sides, and they are distributed with equal probability all over the lattice. The advantage of this model for analyzing this multi-valuedness of our functional and the related vertex divergence, as we will see, is that this model can be solved exactly within DMFT. And in fact, we get an exact expression for the, I call it now, interacting Green's function. So I should always say in this section of my talk, disordered instead of interacting. However, I will stick mainly to interacting because I'm so used to correlated systems that I will make hundreds of mistakes if I really try to always label it in the right way. So the important point is that this fully interacting Green's function here can be written really as a functional of the non-interacting Green's function. So basically, we can plug in here any non-interacting part of the lattice, and this will give us the correct result for the interacting Green's function. And then together with the Dyson equation, this explicit expression allows us to eliminate the non-interacting Green's function. And that means we get a quadratic equation now for the self-energy, which depends on this interacting Green's function. And as we all know from high school, a quadratic equation has two solutions. So we immediately see that we get two branches for our self-energy functional. So a plus branch corresponding to this plus sign in front of the square root, and a minus branch. So let us try to analyze and to understand what these two branches mean. So first of all, let's look at the limit W to 0, so to the non-interacting case. That's actually so what happens to this self-energy, and what we observe is that the plus branch indeed goes to 0. And that's good, because in the non-interacting case, we should have a vanishing self-energy. If we look at the minus branch, this for the coupling strength W goes to 0, this doesn't vanish. So this we call now a non-perturbative branch, while the first one is the perturbative branch. There is now, of course, the question, do we actually need at all this sigma minus branch? I mean, it's a non-perturbative branch. It doesn't have the correct limit for coupling strength going to 0. For this, let's look at some numerical results. So this is done now at some temperatures. That's not so important, and we will start at some weak coupling value. So believe me, this is something which I call now weak coupling value. I do not show the phase diagram now. This you have already seen in the talk of Alessandro. So let's look rather at the Green's function of the system. So you see that this Green's function at this weak coupling value is monotonous. That means it at low frequencies it has a rather low value, a rather large value at omega equals 0, corresponding to a rather large value of spectral weight. So let's look now at the self-energy, and this plot needs now a bit of explanation. So we have here a physical self-energy which corresponds to these empty circles. And then we plot in addition the sigma plus and the sigma minus branch of the self-energy. So you can see at this weak coupling, in this weak coupling picture, the physical self-energy coincides everywhere for all frequencies with the sigma plus branch. So it seems that the sigma minus branch is just an artifact and not really needed. However, if we go to strong coupling, we observe that the Green's function develops a minimum at a given frequency nu star. This already indicates the trend to going to a more insulating behavior, as at 0 frequency, the Green's function tends to go to 0. So we are still here at this parameter value rather far away from the really insulating system. However, the trend is already going to an insulator. if we now look at the self-energy, we see that the physical self-energy is again monotonous, so it always decays, and it should be for a system of binary disorder. However, we see that exactly at the minimum of the Green's function, we have to change the branch from the sigma plus to the sigma minus in order to recover really the physical Green's function, really the physical self-energy. So that means if we go to stronger coupling, to a regime where we already see the closing of the gap, we have to consider the non-perturbative branch of this self-energy functional. So that means it's not just an artifact which we can throw away, but we really have to, we really need this, we really have to consider this. Yeah, so that's the crossing, and we have here this branching. So that means that what I said, that we have to change at this frequency the two branches. So the question is now, how is this now related to these vertex divergences, so to these two particle quantities mentioned by Ale? And we are now in a very good situation because we have actually an analytic expression for this sigma of G, and as already Ale pointed out, this irreducible vertex can be calculated via a beta-cell-beta equation, but it can be also obtained via a direct functional derivative of the self-energy functional with respect to the interacting Green's function. And this is a very simple task, which you also know from high school. So we get basically this expression, and again we get, of course, since we had two branches of the self-energy, we also get two branches of this vertex. What we observe is that this vertex obviously diverges if this square root here becomes 0. However, as we can see, this is exactly the value where the two branches of the self-energy cross. Yeah. So let's look again at some results for the vertex. So again, we see at the weak coupling value, the physical vertex, which is the empty circles, coincides with the gamma plus branch, while at larger values of the coupling, we go now to the gamma minus branch for low frequencies. However, what we can see is that now this is not a crossing of branches like in the self-energy, but this crossing, so if I would call it crossing, so this crossing happens actually via a divergence. So not a real crossing, but the gamma plus branch goes to plus infinity, while it changes to the gamma minus branch going here to minus infinity at this value of nu star. And the same is true even for stronger values of the coupling, where, however, in addition, you see a second divergence, which is now really related to going to the insulating behavior, because at very small at small frequencies and strong coupling, a gap opens in the spectrum, which means the Green's function at 0 frequency goes to 0, and that causes this second divergence in the irreducible vertex. So the take-home message of this first model system is basically a minimum in the Green's function of this model, which indicates a trend to going insulating, corresponds to a crossing of branches in the self-energy, and this crossing of branches implies vertex divergences in the irreducible vertex, where at this divergence the crossing of branches happens. The second model I want to look at is the Hubbard atom, so the atomic limit of the Hubbard model, where you set the hopping to 0 and you focus basically on only one lattice side. And in this model, you have analytical access to basically all the correlation functions. So that's a big advantage. So basically, we consider this model now exactly at half filling. The only thing which you do not have here is an explicit expression for the self-energy functional as you had it for your binary mixture. There is one word of warning. Sometimes in the literature, you find a functional for this atomic limit. And the reason is that this formula for the interacting Green's function resembles very much that of the binary mixture. However, this is of course not the correct functional of the atomic limit. And this can be seen by a very simple argument. If you would know an analytic functional for the atomic limit, you would know the analytic solution of the Hubbard model, because the self-energy functional is a universal quantity, which doesn't actually depend on this non-interacting part here. So that means if for this part of the Hamiltonian, you know the Latinger ward and the self-energy functional, you know it for all possible models with all non-interacting parts. This is something we, of course, do not know. And that means we have to resort to numerical investigations. And now
you have 5 more minutes of talking time.
Thanks. So for this, we resort now to this mapping of G0 to G, where we have many G0s which are mapped onto the full interacting Green's function. We are an impurity solver from which we get then the branches for the self-energy. So we have basically to solve an inverse problem coming from a known Green's function to a non-interacting finding non-interacting ones, so physical one and unphysical one. So I will not discuss how we did this. So basically it was done by Hirsch-Phi quantum Monte Carlo solvent using this in the inverse way. Let me go right to the results. So basically what I show here are these unphysical Green's function we identified, and we identified 2 of them, so 2 non-interacting unphysical Green's functions, and we compare them to the physical one in that way that we plot here the G0 normalized by the physical one as a function of u for the lowest, the second lowest, and the third lowest Matsubara frequency. This plot is a bit complicated, so there are several symmetries of these Green's functions for negative and positive frequencies. So therefore, sometimes we have only one branch, only showing positive frequencies. Sometimes we have to show also the negative frequencies because they are, the results are different from the positive ones. What we observe, and what is the important point here, is, however, that we observe these crossings here. So if we have now a closer look at these crossings, what we see is that they happen with a certain power law behavior. So for this first crossing here, we see that only for the first Matsubara frequency we observe a linear behavior, while for all the other Matsubara frequencies we observe a square root behavior. And that means if we define a minimal exponent for this crossing, this minimal exponent is 1, and it's only taken by the first Matsubara frequency. For the other crossing, that's the second crossing, so we found for our second orange solution, we find actually a crossing with a square root like behavior here. So the exponent is here 0.5. And this exponent is now, we also find this exponent if we look at the real part, which appears on the other side of the crossing, where the imaginary part would cross with an exponent of 1, but the real part restores again our crossing of 0.5. So we can see that for this orange divergence, for this orange crossing, all frequency cross with this exponent of 0.5. So how is this related now to the vertex divergences? And this is my last slide now. So fortunately, in the atomic limit, we have for the irreducible vertex an explicit expression of this irreducible vertex. And this is very complicated. So just look at the colored parts of this vertex. So first of all, it's clear if this denominator vanishes in our vertex function, we get a divergence of the vertex. Since this depends now on the Matsubara frequency nu squared, this will be a localized divergence, which happens only at this single Matsubara frequency. If we now use the definition of the Matsubara frequency, this defines, of course, for each Matsubara frequency a divergence line in our phase diagram, which was already shown by Alessandro. And this implies that we have an infinite number of such red divergences, where the irreducible vertex diverges at just a single frequency. If we look now at one of them, like at the first Matsubara frequency, we find that this divergence happens at the u value of rather pi over square root of 3. And now we see that's exactly the value where we had the crossing between the physical and the unphysical non-interacting Green's functions. Similar, if this denominator in this irreducible vertex diverges, so becomes 0, we get another type of vertex divergence, which is now a global vertex divergence, because this denominator doesn't depend on the Matsubara frequency, on the fermionic Matsubara frequency nu. And again, if we look at the solution of this equation for some beta value, we get a u of 2.57. And if you remember the previous slide, you can see that this exactly coincides with the second crossing of physical and unphysical G-zeros. So that means we have shown with this that we have that the crossing of unphysical and physical branch of the self-energy functional implies vertex divergences also in this atomic limit model, like for the binary mixture. But what we also realize now is that the type of vertex divergence, local versus global, is defined by this exponent in this power law, how the crossing of the G-zeros appears. These were, of course, now just is now just a numerical finding. However, in this paper here, with Ole Gunnarsson, Thomas, and Alessandro, we managed actually to give an analytical proof of these two statements, not only for the atomic limit, but in a very general situation. So with this, I come to just to the take-home messages. So basically, a crossing of branches of sigma of G implies a vertex divergence. And second, the type of crossing of these two branches defines the type of the two divergences, so local versus global. With this, I thank you for your attention, and I happily expect your questions.